Unit 10 is basically, well, it's chapter 29 and 30. And chapter 29 is all about the effects of magnetic fields. And chapter 30 is about the causes. What causes magnetic fields? So this is what do magnetic fields do, and then how do you make magnetic fields in the first place? So it's kind of an interesting way to go about it. So what do magnetic fields do? Well, magnetic fields apply forces to objects that have charge and are moving. And the equation that describes it, well, there's two equations that describe the basic effect, or really the force that magnetic fields apply. And that is this. The force on a free-moving charged particle is equal to Q. Now that represents the charge on your moving charge times its velocity crossed with the magnetic field. And remember, in chapter 29, they just kind of say, hey, there's a magnetic field here. They don't really tell you how it got there. And they just say, it exists. And magnetic fields do exist. Here's the effect that we've observed they have on free-moving charged particles. So you really have to understand this cross product. You really have to understand cross products in three-dimensional space and how to use the right-hand rule. And one of the things you'll be expected to do, if you have a magnetic field, here's 3 lines of magnetic flux, and if you have a charged particle, say a positive charge, and it's moving like this, what is the direction of the force? Well, you can get the magnitude of the force by saying QVB sine theta, where theta is the angle between the velocity vector and the magnetic field vector. Here's the velocity vector as I've drawn it, and so if I kind of stay parallel to these other ones, here's the angle theta. So it's the angle formed if you hook them up tail to tail. I mean, that's what you do when you figure out cross products. The magnitude of cross product is the magnitude of this vector times the magnitude of this vector times the sine of the angle between those two vectors. And then, of course, we have the scalar, which is just the charge on the object here. And then you use the right-hand rule to figure out the direction. And the right-hand rule tells you, the way I like to teach it is, you take your right hand and you point your fingers in the direction of the first vector, which is the velocity vector, and you cross it over to the magnetic field line, and how you have to orient your hand will determine how you orient your thumb, and your thumb tells you the direction of the force. So V, well, to cross over to B, I have to put my hand like this and cross over like that. So it's V, cross over to B. My thumb is straight down into the paper. So the direction is into the paper in this case. Remember, into the paper, we go like that, and out of the paper, we draw a little dot like that. And this, you can think of these as the tail feathers of an arrow moving away from you, and this is the point of the arrow moving towards you, into and out of the paper. And by the way, all this right-hand rule stuff that is in electromagnetism, whether it be, it's all based on this. This is kind of the equation where everything starts. Now, we also had another force, kind of a basic force, and that was the force of a magnetic field on a current. So if you have a wire like this, and you have a current flowing through it, I, And let's say the current that's in, let's say we'll put a magnetic field in here. So here's our magnetic field. And what do these little crosses mean? That the magnetic field is into the paper. And we said that, well, the force, well, this wire with current flowing through it is going to experience a force IL cross B, where L is the length of the wire that's in the magnetic field. Now, current really is a scalar. I mean, it's just how many charges are passing through a cross-sectional area at any given time, and that quantity is a scalar quantity. But this really represents the displacement that those charges are going through. So a charge, if you look at a moving charge in the wire, it'll go from here to here. So that's its displacement due to the fact that it has a current. So again, this is how much current you have in amps. It's how long the wire is. It's in the magnetic field. And this is the strength of the magnetic field. And again, it's a cross product. Now these two equations are very similar. Now I'm not going to rederive everything here. You can read the book or go back and look at the old lectures online. But we used this in conjunction with the drift velocity equation and all that to get this. So these two equations are really saying the same thing. This is for an individual charge moving in a magnetic field. This is for a whole stream of charges that are moving in a magnetic field, constrained to move within the wire. They can't freely move. They have to stay in the wire. One of the things that we talked about with this was that what if your wire is bent? What if you have a magnetic field like this? Well, it should be a uniform field, but it doesn't really matter. And we have a wire that kind of goes like this. So the current goes like this, like this, like this, like this. So that in here, the length of the displacement was in a straight line. Didn't vary, but here it's varying. So what we can do is say that the force on this wire is equal to, well, we have little tiny forces on the wire, and it's going to be equal to the current. Now the current's the same everywhere in the wire, and we call that a steady current. And then we'll make each one of these little things DLs cross B, or the book might have used DS. I don't know, DS, DL means the same thing. And we're going to integrate this. Well, if the magnetic field is constant and the current is constant, you can just look at this. And what are the sums of all these little DLs? DL plus DL plus DL, it's a vector sum. Well, when you add all this up, it's just the length from where you start to where you end. Here, from here to here. So it's just the force on, basically what you get is you get this equation where you get the total force is going to be equal to I L cross B, where L is just the total displacement from your starting position to where you finish. So all this winding around stuff didn't really have much of a effect. Unless, of course, you wind around like this, but you come all the way back to where you started. Well, now your effective length is 0, and you'll have a net 0 force on this wire if you have a closed loop of wire. If you end up where you started with your loop of wire that has a current in it, even if it's I drew a figure 8 here, but it doesn't really matter what you draw, that will be 0. In other words, and a way of saying that is that the force on a closed loop, I dl cross B, well, that will equal 0. Okay. You won't have a net force on it. However, you will, if you have a loop of wire in a magnetic field, you will get a torque. And we derived that as well. And again, if I rederive everything, this review lecture will be 4 hours long. So again, I'm just kind of reviewing the basic results that we got. So we will have a torque on a loop of wire. So if we have, and I think we used a square wire, but it doesn't have to be a square wire. Let's put a magnetic field like this into the board. Why do I always put a magnetic field into the board rather than out of the board? Because this is easier to draw. It's easier to see. Doesn't matter what direction I make the magnetic field. So I just make it, for convenience sake, I put it into the paper to make it easier to visualize. And if I have a loop of wire that's embedded in this, well, if I do it like this, actually this is not a great example. What happens is that I have a length of wire here. Let's say the current is going in a loop like this. Now you say, how can a current go in a loop? Well, just put a battery in there or something. We're not drawing the source of current. Okay, we're just saying there is current. There is charge flowing in a circle around here. And well, you have I, and we have F equals IL cross B, and we can do this for each section of this loop. So I'll use the right-hand rule. I cross B. So the force on the wire is up like this. So there's my force. And then I go I cross B. So I cross over to B. So my thumb is that way. I cross B. Oop, now my thumb is down. So you can see here that the forces, and if you do the same thing here, these forces are all canceling each other out. So you have no net force. And that's what we should have gotten. I mean, that's what we just said right here. If you go in a closed loop, the net force is going to be zero. The net magnetic force is zero. But here, this is really uninteresting. But if you take your loop of wire and you rotate it 90 degrees, or if instead, in my imagination, I take these magnetic field lines that are down right now and I just rotate them like this, or I rotate my point of view by 90 degrees, and I rotate the loop by 90 degrees. Let's keep the loop in the same view. But now I lay out this magnetic field is now in the same plane described by the loop of wire. Well, now something very interesting happens. If I look at this part right here, since the current here is parallel to the magnetic field line, there's no force, right? Because the force is a cross product. It's IL cross B. Well, if L and B are parallel to each other, your cross product is zero. But here the cross product is perpendiculars. And so if I go I cross over to B, I get a downward force. So that represents the force downwards on that wire. And of course up here, as the current moves in this direction, again the force is zero because L and B are 180 degrees apart, and sine of 180 degrees is zero. But then I come down here through this part, and if I go I cross B, well, let's see, it's hard. I'm going to rotate the paper. I cross over to B, my thumb comes out. So really this creates an outward force, and I get a torque. And if I put this loop of wire on a shaft, okay, and put it with a bunch of other loops and design this thing, just do a bunch of engineering, I've created an electric motor. Electric motors just have currents going through wires that are embedded in magnetic fields, and they get a torque put on them, and that torque will make things spin. Now there's all kinds of complicated things going on in a motor. You have to reverse the direction of the current every 180 degrees of rotation. Otherwise, the thing will just flop back and forth like this, and that's not very useful. But if every time it rotates 180, you flip the direction of the current, it'll keep twisting in the same way. And if you have a whole bunch of these loops and you kind of fold them around a cylinder, you'll get a nice, smooth, continuous torque in your electric motor. That's a really great branch of engineering, is electrical engineering. They study how to make really efficient motors from currents and magnetic fields. It's an engineering marvel. Well, we did all the math for this, and again, I'm not going to repeat, but the torque on it was just equal to, I A cross B. Now, this was a very clever little thing we observed about why it's the current times the area. This A is the area described by the loop of wire. So here we have this loop of wire in this plane, and it has a certain area. And the amount of torque depends on how much current you have, but it also depends on the total area that's contained by this loop. Here's that area. Now, what's the direction of the area? Well, when in doubt, use the right-hand rule, and that's what we're going to do. If you take the current flowing like this, you circulate your fingers in the direction of that, and so you have an area vector that's up. So this area vector has a magnitude of the area of this rectangle. It doesn't have to be a rectangle; it could be a circle. Most motors actually have circles like this. Why did we use a rectangle? Because when we derived the torque, it was much easier to derive the torque equation using a rectangle rather than a circle. But one could use a circle or an amoeba shape or whatever you want in there. Amoeba wouldn't be very efficient, but it could work. The direction of the area vector is defined by circulating your fingers in the direction of the current around your loop. Your thumb points in the area vector. The magnitude of your area vector is just the total area described. Okay? And so in this case, what would be the direction of the torque? Well, I is this way, so I'd go I cross over to B, and the direction of the torque would be straight up. In other words, this thing is going to swing around like this. I don't know if you can kind of visualize that the way I've drawn it, but it's going to rotate, around. It's going to go into the paper, out of the paper, into the paper, out of the paper over here. And of course, we describe the direction of angular motion with the right-hand rule. The right-hand rule is very, very useful in a lot of different things. And so that shows the orientation of the twisting, the orientation of the torque. Okay? So so this all comes from, well, here's kind of, we have one more equation to go over, but the torque equation really comes from the force equations. And if you go through it, it all kind of makes sense. Oh, one thing I would like to mention in the review is, what are the units? We have this this equation right here for force. Well, you could take this equation and solve it for B. So B equals F over QV. All right, and let's not worry about the vector nature of it. Let's just look at the units here. This is units of newtons, and this is coulombs, meters per second. And a newton coulomb per meter per second is called a Tesla. No, it's not named after the really cool car. Okay, it's named after the scientist, and of course the really cool car is also named after the scientist. And by the way, look at this. What is a coulomb per second? A coulomb per second is an amp. So you can also say that that a Tesla, we use a capital T for Tesla, is equal to a Newton amp meter. So either way you want to look at it, which does make a lot of sense, right? I mean, if you solve for B here, you get B is equal to F over I L. Well, that's newtons per ampere meter. Oh, yeah, there you go. Okay. All right. The last thing that was talked about that you in chapter 29 is, well, what happens to a moving magnetic or a moving charged particle in a uniform magnetic field? So let's have a uniform magnetic field again here. See, don't you wish you were watching this at home and you can just go at double speed? Sorry. But here we're going to inject a positive charge at a certain velocity. And what you're going to do is you're going to get a force. So remember, the magnetic force is always perpendicular to both the magnetic field and the velocity vectors. Right? That's what so you go V cross over to B. I know the force is going to be like this. So there's my magnetic force. But the magnetic force is always going to be perpendicular to the direction of motion. And we have dealt with forces that are always perpendicular to the direction of motion. They're called centripetal forces. They're center seeking. This thing, if it's freely moving, it's going to move in a circle. So you can say that that force equals, let's just look at the magnitude, QBB, right? That's going to be equal to mv squared over r. Now this little observation, just setting the magnetic force equal to the centripetal force, you can just memorize that and solve just about any problem they're going to give you on this. You can, if they give you the mass and they give you the, the magnetic field and the charge, you can, well, I mean, you can solve for any of these. They have to give you enough information to solve for them. But there's a couple of interesting things. V over r, well, that has units of radians per second, doesn't it? The speed divided by the radius is the angular velocity of this guy. How many radians per second it's sweeping through as it moves around this circle. And so V over r, well, if I cancel this out, it's just QB over m. And so we call this omega. This omega is called the cyclotron frequency, I think, or what was it called? Oh, the correct vocabulary. Cyclotron frequency. Well, there are these things called cyclotrons that it's the cyclotron frequency. And of course, if you know that omega is, well, from that you can get the period. And the period is equal, well, the period is always equal to 2 pi over the angular frequency. And so you can say that the period of this motion here is equal to 2 pi. Remember the period of a pendulum had a 2 pi in front of it, and the period of a physical pendulum and a mass spring system, it's always got a 2 pi in front of it, times the square root, or times, over omega, and so that'll be m over qb. Right, you just flip this thing over. So if they ask for the period of this, and you can get it, or the cyclotron frequency. One thing too, if this thing is in a, if it has a component of its velocity vector that's parallel to the magnetic field, well, that component of its velocity doesn't change direction. Only the velocity that's in the plane, only the component of the velocity that's perpendicular to the magnetic field vector gets turned or gets its direction changed, which means that if this charged particle was not only had a component like this, but a component that was out of the paper, it would spiral and come towards us like this. I don't know if you can see that. Or if I tilt this, well, it would spiral through space like this. Okay. And they've got a much better drawing in the book, so do review the book. Okay. So that was chapter 29. Now we get to chapter 30. Chapter 30 was all about where magnetic fields come from. And there is one law that describes it all, and that's the Biot-Savart law. And I don't know, I've been teaching this class for 21 years, and I've been calling it the Biot-Savart law. I don't know if I'm pronouncing it right or not. If I'm pronouncing it wrong, I don't want to know, so I'm too old to change. And it's a heinous equation. In fact, some students call it the heinous equation. But it says that, okay, B, what is the cause of magnetic fields? Current. Anytime you have a moving charge, you have a magnetic field created by that moving charge. It's the law of nature. And this describes it. Well, let's say I've got a wire, and it's got a steady current of I. We're just dealing with steady currents in this class. Steady means just not changing with time. And there's a little point in space, and we say, okay, well, right here, there's a current, and I want to know how much magnetic field is created by this little tiny current, or this little tiny segment of current way over here. So we'll start off with a little differential element of it, and then of course we'll integrate. But first of all, it depends on the length of the wire that has current running through it. So that's ds, and we could use dl. The direction of this depends on the direction that we point to from the wire, and we call that direction r hat. And this is ds. This is a little tiny ds. This is r hat, and so you go ds cross r hat. So I go ds cross r hat. That means my thumb is going to point out of the page. And so the magnetic field created by this little wire, or this little segment of current running through this wire, is going to be out of the page on this side. Now if I was over here, ds cross r hat, my thumb would be into the page, so the magnetic field would be into the page over here. But it's out of the page on this side of the wire. And of course, if I'm on top of the wire, if I'm out here, if I go ds, ds cross r hat, my thumb would point sideways. So really what this is implying, this is what gives us, this ds cross r hat is what gives us this loop of magnetic flux. Comes out of the paper, comes over the top, goes into the paper, goes underneath, and we're going to get a continuous loop of magnetic flux. Okay, and it all comes from that ds cross r hat. Of course, it does matter how far away. If the farther away we are from this little differential element of length over here, well, we get over r squared. And of course, it depends on the current. Oops, leave enough room here. And the rest of it is just constants of nature, which I'm not going to worry about. I'm just going to give them to you, and you just have to accept. Mu naught over 4 pi. Now, we've done this before. Mu naught, we had epsilon naught. We had big G was the universal gravitational constant. It's just, what this is saying is, look, to create magnetic field, you have to have a current moving, and the amount of magnetic field, the strength of magnetic field, it depends on how long the wire is, what your orientation in space with it is, how far away it is, and how much current you have. Everything else is just constants of nature. Well, now we're going to add these all up. So we get B is equal to mu naught I over 4 pi, there's all your constant stuff, times the integral of ds cross r hat over r squared. This is very cumbersome to use. I have seen a couple of years ago there was a problem where you had to use the Biot-Savart law to figure out the strength of the magnetic field. The nice thing about it was that it was symmetric. It was symmetric so that r squared came out of the integral. And then this was pretty easy to figure out. So I've never seen a hard problem with Biot-Savart law. You know, like some of the examples in the book were actually pretty challenging. On the AP test, I've never seen a hard one. So don't be intimidated by this. Study it. You should know it. You should understand the bits and pieces of what it means. Like, what does the ds mean? What does the r hat mean? Okay, mu naught over 4 pi. What is that? Okay, it just makes this just makes the units work. And mu naught, what is it? 4 pi times 10 to the negative 7. By definition, it's a definition, not a measured or calculated quantity. Anyway, using the Biot-Savart law, we came up with a much more commonly useful equation. There were a bunch of examples we used in the book where you derived expressions, but the one that is used the most that you should memorize is, what if you have a long straight wire? Long straight wire. Well, we used the Biot-Savart law to do it. This is in your book. This was example 30.1. They did it for a short length of wire, and then you just extrapolate that out to be a long length of wire. Long length of wire means that it acts like an infinitely long wire. I mean, it's not infinitely long, but it acts like one. And what you get is, because of this ds cross r hat, you end up with a circle. Now let's show the current. It's going like this. And what you do is use the right-hand rule for long wires. You grab the wire with your right hand. Your thumb is in the direction of the current, and your fingers will curl around it like that. And so that's the direction of the magnetic field. It will start back here, go down in front, and up in the back. So when I draw loops like this, if I leave a little gap, that implies that this is behind the wire. That's the way I draw it, and you know, it makes it a little bit easier to understand. So this is in front of the wire right here. So sometimes I'll make this a little darker, and this kind of goes behind. All right. So, and using the Biot-Savart law, we also got the magnitude of this. If this is A, or you can use R if you want, R for radius, but A, in this case, A is the distance, the shortest distance from the center, or from the wire out to where this guy is. You said that B is equal to mu naught I over 2 pi A. And the direction of it is right-hand rule for long straight wires. Grab the wire with your right hand. By the way, whether it's solenoids or wires or whatever's kind of straight, use your thumb, and whatever goes in a circle or curls around, use your fingers for the right-hand rule, using the right-hand rule. So this one, you should know cold. The strength of the magnetic field created by a long straight wire. Notice that it's 1 over, you know, if I make A twice as far away, the strength of the magnetic field will be half as much. Okay. So that's long straight wires. Now, then one thing that they really love to give to you, and this was, again, I'm not going to rederive it. I don't want to rederive very much today because it's just too much to review. What if I have 2 long straight wires like this? Let's say they're both, this is I1, and this is I2. Well, it turns out that, look, I1 creates a magnetic field, right? Because long straight wires create magnetic fields. But wires in a magnetic field feel a force. So this wire creates a magnetic field that applies a force to this wire. So the magnetic field of wire 1 applies a force to wire 2. But wire 2 does the same thing. Wire 2 creates a magnetic field that applies a force to wire 1. And Newton's third law is going to be kept in that they're going to be equal and opposite. Turns out that long, straight, parallel wires, where the currents are in the same direction, attract each other. They apply forces like this, and the magnitude of that force is equal to mu naught times I1 times I2 over 2 pi a, and a is the distance between those wires, times L. And L is the length of wire from here to here. Quite often they'll give you the force per unit length, which means that they just give you F over L equals something. I think that's what I do on the test. And this equation was derived by figuring out the magnetic field due to a long straight wire, and then figuring out the force on a wire using F equals IL cross B. Okay, so if you want to know. Now, by the way, it's kind of a good thing that wires with currents that are parallel attract each other, because lots and lots of wires, like big fat cables of wire, are not one big thick tube of copper. They're made out of thousands of strands of wire. So let's take a look at a cable of wire. Let's say you've got like 500 or 600 little strands of wire, and they've all got current running through them. Well, what do these currents do? These are all parallel currents. They squeeze, the wire actually squeezes itself together. The stranded wire squeezes itself together, which is really nice. What if they repelled? Okay, you put a current through them and poof, the wire would explode. The stranded wire would all repel, all the stranded wires would repel, and so that's not good. So nature was very nice. This was very nice of nature to arrange itself that we can have stranded wire. Okay. The next big idea was Amperes Law. And we used a long straight wire to derive this thing, and this is kind of the Gauss's law for magnetic fields. The Gauss's law for electric fields, this is what Amperes Law does. And it basically says this B dot ds is equal to mu naught times I enclosed. Now this is Amperes Law. Then we added something to it. Mu naught times this thing we call displacement current, which is really epsilon naught times the rate of change. Whoops. This is the rate of change of electric flux. And the only problem I've seen where we deal with this is when you have a capacitor that's filling with charge. And a capacitor filling with charge acts just like the wire that feeds into it. So the rate at which you change the electric flux times epsilon naught is really the rate at which we're adding charge to the capacitor, which is really the current that's leading into that capacitor. But let's just talk about this part right now. We use this a lot. I guarantee you every free response test in magnetism will have an Amperes Law problem, where you're going to have to use Amperes Law to figure out the magnetic field given a certain current. So what is this little integral sign here? This is closed. And what is ds? a closed length. ds is a closed displacement, and this is always going to form a loop. And there are many examples of using Amperes Law to figure out magnetic fields for different situations. And I'm not, this review is already 40 minutes long, so I'm not going to review all of them. But remember that, if I've got some kind of current distribution, this represents like a current flowing through a wire. Maybe this is some kind of weird wire that's got current flowing through it. You want to know what's the magnetic field at some location. Well, you draw a loop that goes right on top of the magnetic field lines. Remember, magnetic field lines, if I are going to form loops around the current. So I know it's going to, if my currents are going like this, magnetic field is going to form a loop around it. So you draw a closed loop so it exactly matches, it goes right on top of that magnetic field. And when you do that, you're going to get B times some length. Now in this case, it would be 2 pi r. But remember, we did it for a solenoid and we did it for other things, and it's not always 2 pi r, it's just usually 2 pi r in all the different examples we do. And then you divide both sides by 2 pi r. Figure out how much current is inside. What does this represent? The current that's inside my loop. So you're going to have to do some kind of calculation to figure out how much current is inside. Now if you're outside, way out here, all the current is inside my loop. But if you're on the inside, some of the current is outside your loop. You don't want to include that in your I enclosed. Okay. And let's see here. Almost done. Oh, I ran out of paper. I think I can squeeze it in over here. Talking about solenoids. Solenoids are really important. They're used all over the place. One of the most common electromechanical devices is a solenoid. Whoop. And this is the little trick of how you show a solenoid. And here's what happens is that if I've got a current flowing through here, what happens on the outside? Let's say that this solenoid is ideal. It's an ideal solenoid. They don't really exist, but we're going to say, hey, we're going to come really close to an ideal solenoid. Well, the magnetic field out here and out here basically gets canceled out. Here we have a wire going into the paper, a current going into the paper, and here we have the current coming out of the paper. And they kind of serve to cancel each other out on the outside. But on the inside of the solenoid, all these loops add up. The magnetic fields that these currents create all add up. They add up. So that's why you get a really super intense magnetic field. It's called an electromagnet, right? Now these field lines shouldn't cross, I'm sorry. But so the strength of the magnetic field inside your solenoid, well, it's equal to mu naught times the number of loops per unit length divided by the length times the current in the wire. Sometimes this N over L is called like this little N looking thing. It's a Greek letter, but it doesn't depend on the radius of the radius of the solenoid. Now the amount of magnetic flux does. We have a definition for magnetic flux. B dot dA. This is kind of one thing about B, and it's the same thing with the electric field. The magnetic field strength, in a way, if you're going to draw it as lines of flux, it's a measure of how concentrated those lines of flux are, or how many lines of flux per unit area you have. You multiply that by the area, and you get the total amount of flux. Now here, the magnetic field inside a solenoid is uniform. So this integral, this is just going to be B times A. And of course, A, the area of this solenoid is just pi r squared, the radius of it squared. So you can pi r squared for that. And you get, but the important thing is to remember that it's B times A. Now, what do these field lines do? Well, they come way out like this. They bend around in space, and they come back in like this. And if it's a real ideal solenoid, if you're kind of out here, you'll measure a pretty strong magnetic field. But you get out here, the magnetic field gets really super weak. Really weak out here. In an ideal solenoid, you would say it's 0 out here. But in the real world, you don't have, you have things that only approach being ideal. Now remember, magnetic field lines always come in loops, and that gets us to the last idea that I'm going to talk about in the review. And that is Gauss's law for magnetic fields. Remember, for electric fields, we said the amount of, this is magnetic flux, the amount of electric flux is equal to E dot dA. And if we enclosed an area, we said, okay, this area is going to enclose a certain space. The net flux coming out of that volume is equal to the charge enclosed by that volume, or by that enclosed by that area, that closed surface area, divided by epsilon naught. But since magnetic field lines, to the best of our knowledge, always come in loops, you can't enclose positive or negative magnetism. It doesn't exist. You can't, remember we said this is like the North Pole and this is like the South Pole of a magnet. You can't enclose a North Pole. All you can do is say, okay, here's the North, here, I create a new North Pole and a new South Pole. So there will always be, so in other words, magnetic flux, if you enclose a space, it's always going to be 0 net flux. 0 flux given. So Gauss's law for magnetic fields really aren't very, you don't really use them computationally a lot. They're just it's a way of saying mathematically that things like magnetic monopoles do not exist in nature. At least we have never observed them existing in nature. So if you want to win a Nobel Prize, go out and find a North Pole without a South Pole, you know, magnetically speaking. Never been done. Okay, so, well, that was a long haul, but basically, here's kind of a, I don't know if this will fit. This is kind of what I was using as a little bit of an outline. I mean, this is an equation list, but, oh, I forgot to put this. This is magnetic flux. Magnetic flux for a closed surface, B dot dA equals 0. Oh, magnetic flux is measured in Webers, and a Weber is a same thing as a Tesla meter squared. Right, from I just got that from the equation here. So there you go. That is all.